Greetings, fellow students. We are Group 1 of Basic Calculus and Grade 11 Section B. And in our tutorial, we'll discuss how to find the antiderivative of a function. The antiderivative is essentially the reverse operation of differentiation. When we differentiate a function f of x, we get its derivative denoted as f prime of x. Conversely, the antiderivative or integral of f prime of x is f of x. So f of x serves as the antiderivative of its derivative f prime of x. For a general function f of x, its antiderivative is represented by a capital F of x. Thus, capital F of x is the antiderivative of f of x, and f of x is the antiderivative of f prime of x. This explanation should offer a clear understanding of what the antiderivative entails.
Let's consider the scenario where we possess the second derivative of a function and aim to determine the first derivative. Furthermore, we can continue along this path. My intention is to provide you with a summary of these various symbols and operations. When moving to the right, our focus is on finding the antiderivative. Conversely, when moving to the left, our objective is to find the derivative. Integration is the process of discovering the antiderivative. The process of finding the derivative is termed as differentiation. Hopefully, this encapsulates all the necessary information regarding this topic. Now, we define capital F as the integral of the derivative of f of x, resulting in capital F plus c. The constant of integration is always included, though we won't delve into that here. What I'd like to clarify now is what constitutes an indefinite integral. An indefinite integral, often denoted without limits of integration, provides a function, usually in terms of x, but it could also involve other variables like y or z. You can easily recognize an indefinite integral by its lack of integration limits. Now, we know that the derivative of x to the power of 4 is 4x to the power of 3. According to the power rule, the derivative of a variable raised to a constant is the constant times the variable raised to a constant minus 1. Well, the antiderivative of a variable raised to a constant is going to be that variable raised to a constant plus 1, divided by the constant plus 1, and then plus c, the constant of integration. So that's how we define the antiderivative of a variable raised to a constant. So let's find the antiderivative of 4x cubed. Now, the variable is raised to a constant, that's x to the power of 3. So what we're going to do is we're going to add 1 to the exponent. So it's going to be 3 plus 1, and then we're going to divide that by that result. So it becomes 4x to the power of 4 divided by 4, and this gives us the original function x to the power of 4. But we need to add the constant of integration, plus c. If you were to find the derivative of x to the power of 4 plus d, x to the power of 4 will become 4x to the power of 3. When differentiating a constant, it yields 0, essentially maintaining the same expression. Therefore, whenever seeking the indefinite integral or antiderivative of an expression, it's crucial to include the constant of integration. The only instance where the constant of integration isn't a concern is when calculating the indefinite integral, which results in a numerical value. Apart from that scenario, whenever obtaining a function, remember to append plus c when determining the indefinite integral or antiderivative.
So now let's work on some problems. Go ahead and find the antiderivative of the following functions. Integral of x to the 5th dx, integral of 5x 8th dx, and integral of 9x squared dx. Feel free to pause the video and work on these examples. So for the first example, we're just going to add 1 to the exponent of x. And then we're going to divide by the exponent plus 1, and then add the constant of integration. So that's x to the 6 over 6 plus c. For the next example, it's going to be integral of 5x to the 8th power dx. We're going to take 5 outside the integral, and then we're going to add 1 to the exponent 8. That becomes 9, and divide by 9 plus c. So that becomes 5x to the 9 over 9 plus c. Now for the third example, We can do the same thing as the second example. Take 9 outside of the integral sign, then we add 1 to the exponent of x, which is 2, then divide by 2 plus 1. And return the 9 to the numerator. 9x cubed over 3 plus c. We can actually still simplify this further, since both 9 and 3 are divisible by 3. So that becomes 3x cubed over 1 plus c, which is just 3x cubed plus c.
For the next one, it's going to be 8x raised to the power of 4 over 4 plus c. And we know 8 combined by 4 is 2. So this makes it 2x raised to the power of 4 plus c. So as you can see, it's not that difficult to find the antiderivative of a function. So go ahead and try this one. F of x is x cubed minus 4x squared plus 8x. To find the antiderivative of this equation, let's integrate each term individually to make it much easier. So the antiderivative of x cubed is x to the power of 4 over 4. For negative 4x squared, the antiderivative is negative 4 times x to the power of 3 over 3. And of 8x is 4 times x squared. To get the constant 4, we divide 8 by 2. Putting it all together, the antiderivative becomes 1/4 times x to the power of 4 minus 4/3 times x to the power of 3 plus 4 times x squared plus c, where c represents the constant of integration. Remember, simplify your final answer so that it becomes more accurate.
Let's try another problem. So let's say f prime of x, that is the first derivative of x, or rather the first derivative of f. Let's say that's equal to 8x cubed minus 6x squared plus 4x minus 7. So given f prime of x, find the antiderivative of f of x. Go ahead and try that. First, let's write an expression involving indefinite integrals. So, the antiderivative of x cubed is x to the fourth over 4. For x squared, it's x cubed over 3. And for x to the first power, it's x squared over 2. And if you have a constant like 7, all you've got to do is add an x to it. We'll talk more about that shortly. And then, finally, plus c. So now, let's simplify our answer. The antiderivative is going to be 8 divided by 4, which is equal to 2. So we have 2x to the fourth power. 6 divided by 3. So this is the antiderivative of our original function. 2x to the fourth power minus 2x cubed plus 2x squared minus 7x plus c. So as you can see, it's not too difficult to find the antiderivative, but there are other things that you need to know.
Go ahead and find the indefinite integral of these expressions. Integral of 5 dx. Integral of 7 d. Let's start with the first one. We want to find the indefinite integral of a constant 5, and we have dx in front of it. So we know it's going to be 5x. But let's see if we can answer this using the power rule. 5 is the same as 5x to the 0. Any variable raised to the 0 power is 1. So 0 is 1 times 5, which is equivalent to 5. Now using the power rule, this is going to be 5. We're going to add 1 to the exponent and then divide by that result. So the result is that you get 5x plus c. So whenever you have a constant, to integrate that constant, just add a variable to it. Now the variable that you should add will be what is given, either dx, dy, dr, or dz, and etc. So what is the indefinite integral of 7 dy? Instead of 7x, this is going to be 7y plus c. For 3z plus 8, it's going to be 3. And the z, the first power, which becomes z squared over 2, 8 becomes 8z, and then we'll write plus c. So we can simplify this as 3z squared plus 8z plus c. In this problem, we'll find the antiderivative of a product of a function. Integral of y squared times 14y cubed minus 8y plus 12 dy. To find the answer, we must first simplify it, so go ahead and multiply y squared with 14y cubed minus 8y plus 12. This will become integral of 14y to the power of 3 plus 2 minus 8y to the power of 1 plus 2 plus 12y squared dy. As a result, we have the products 14y to the fifth minus 8y cubed plus 12y squared. To start finding the answer, let us separate the whole numbers with y so that it'll be easier. So that's 14 integral of y to the fifth dy minus 8 integral of y cubed dy plus 12 integral of y squared dy. Now that it's all cleared up, let us answer. This is equal to 14 y to the power of 5 plus 1 over 5 plus 1 minus 8 y to the power of 3 plus 1 over 3 plus 1 plus 12 y to the power of 2 plus 1 over 2 plus 1 plus c. This is then equal to 14 y to the 6 over 6 minus 8 y to the 4th over 4th plus 12 y cubed over 3 plus c. Once again, we have to simplify the equation. 14 over 6 is 7 over 3. 8 over 4 is 2. And 12 over 3 is 4. So this will equal to 7y to the 6 over 3 minus 2y to the 4 plus 4y to the 4th plus c.
Now, let's focus on finding the indefinite integral of rational functions. What is the indefinite integral of 1 over x squared? To find this, before you integrate it, you need to rewrite the expression. We need to move the variable from the bottom to the top. So, this is x to the negative 2. At this point, we can use the power rule. So we can integrate it by adding 1 to the exponent. So it's going to be negative 2 plus 1, and then dividing by that result, plus c. Negative 2 plus 1, that's negative 1. And after you integrate it, you need to rewrite it again. So we want to get rid of this negative exponent, and we can do so by moving the variable back to the bottom. So that leaves the 1 on top. And then we're going to have x to the first power on the bottom, which we can just leave as x. The negative sign, I'm going to move it to the top. So the final answer is negative 1 over x plus c. Try this equation. Find the indefinite integral of 7 over x cubed dx. Like before, we're going to move the variable to the top. So we're going to rewrite the integral. So this is 7x to the negative 3 dx. And now let's integrate. So negative 3 plus 1, that's negative 2. And then we're going to divide by negative 2. And then we'll have plus c. So next, we're going to move the variable back to the bottom and the negative sign. I'm going to move to the top. So this becomes negative 7. We have a 2 on the bottom, and we have x squared as well. So it's negative 7 over 2x squared plus c. So that's how you can integrate a rational function.
That concludes this lesson of computing for the antiderivative of algebraic functions. With this, we hope that you'll tackle antiderivative with confidence. Thank you, and good luck.